What specific problem does the new method aim to solve?
The new method, Joint Example Selection, JEST, aims to solve the problem of inefficient and costly manual curation of large-scale datasets for pretraining models. By introducing a model-based data curation approach that selects batches of data based on their joint learnability, JEST accelerates learning in multimodal tasks. The method addresses the challenge of slow and power law scaling of large-scale pretraining by efficiently selecting highly learnable batches from larger superbatches of raw data. JEST aims to improve the training efficiency and performance of models by prioritizing examples that are both unlearned and learnable, thus accelerating learning beyond what is achievable by selecting examples independently. Additionally, JEST enables the utilization of small curated datasets to guide the curation of much larger datasets, leading to significant improvements in model performance on downstream tasks.
How does the proposed method work, and can you illustrate it step by step?
The proposed method, Joint Example Selection, JEST, works by selecting highly learnable batches of data to accelerate large-scale multimodal learning. Here's a step-by-step illustration of how JEST works based on the provided text. 1. Model-based batch selection criteria. JEST uses model-based scoring functions to score entire sub-batches of data based on the losses from the learner model and/or pre-trained reference models. 2. Prioritization heuristics. JEST considers 3 scoring heuristics: hard learner, easy reference, and learnability. Hard learner prioritizes batches with high loss under the learner model. Easy reference prioritizes data that is easy for a pre-trained reference model. And learnability combines these scores to upsample data that is unlearned and learnable. 3. Joint Example Selection. JEST samples batches in proportion to their joint learnability, decomposing the batch learnability into conditional learnabilities of each example given other examples in the batch. 4. Efficient scoring and multi-resolution training. JEST leverages online model approximation to score large superbatches efficiently. It uses multi-resolution training to train at both low and high resolutions, allowing for efficient scoring and yielding gains in efficiency. 5. Data quality bootstrapping. JEST utilizes a pre-trained reference model, trained on a small curated dataset to guide the curation of a much larger dataset, enabling strong data quality bootstrapping and surpassing the quality of the reference model on downstream tasks. In summary, JEST accelerates learning by selecting batches of data based on their joint learnability, leveraging model-based scoring criteria, efficient scoring methods, and multi-resolution training to achieve significant gains in training efficiency and performance.
What are the theoretical or practical benefits of using this method?
The theoretical and practical benefits of using the JEST method include significant acceleration of large-scale multimodal learning, surpassing the previous state-of-the-art with up to 10 times fewer flops and 13 times fewer examples. By jointly selecting the most learnable batches of data, JEST improves training efficiency by prioritizing batches that are both unlearned and learnable, leading to faster convergence and better performance. The method allows for the efficient selection of relevant sub-batches from larger superbatches, reducing the overhead of scoring while maintaining gains in training efficiency. Additionally, JEST enables strong data quality bootstrapping by using small curated datasets to guide learning on much larger uncurated ones, resulting in models that surpass the quality of the reference model on downstream tasks. The approach also simplifies data curation by showing that pre-filtering is redundant for JEST, eliminating the need for foundation datasets. Overall, JEST offers a more effective and general replacement for generic foundation datasets, demonstrating the potential for dynamic and online data selection to improve pre-training efficiency and performance in multimodal learning tasks.
How is the method validated or tested?
The method is validated or tested through a series of experiments and comparisons outlined in the paper. The validation process involves evaluating the efficacy of the Joint Example Selection, JEST algorithm, for selecting highly learnable batches during training. This is done by visualizing the learnability matrix and comparing the learnability of sub-batches selected by JEST with brute force Gibbs sampling. The paper also investigates the impact of training on more learnable batches selected by JEST on downstream tasks such as ImageNet classification and COCO image-to-text retrieval. The performance of JEST is compared to previous methods, including state-of-the-art models like SIG-LIP, to demonstrate its efficiency and effectiveness. Additionally, the paper explores the synergies between multi-resolution training and online batch selection, showing how these techniques contribute to the overall performance of the method. The results are presented in figures and tables, showcasing the improvements in training efficiency, flops reduction, and performance gains achieved by JEST and its variants. The method is further validated by comparing it to prior art, including strong clip variants and state-of-the-art models, demonstrating superior performance with significantly fewer training iterations and flops. The experiments also include scaling data curation to show the impact of dataset size on reference model performance and JEST pretraining. Overall, the method is rigorously tested through a combination of experiments, comparisons, and analyses to validate its effectiveness in accelerating multimodal learning and achieving state-of-the-art results.
What results were achieved with this new method?
The new method, Joint Example Selection, JEST, achieved significant results in accelerating large-scale multimodal learning. It outperformed the previous state-of-the-art models with up to 10 times fewer flops and 13 times fewer training examples. Specifically, JEST significantly accelerated learning, reaching the final performance of the baseline after only 2 billion, 1 billion, and 0.67 billion training examples when using filtering ratios of 50%, 80%, and 90%, respectively. JEST also delivered significant gains of up to 6% when filtering 90% of data. Furthermore, JEST set a new state-of-the-art on both ImageNet and COCO datasets, surpassing the previous models while using significantly fewer iterations and less compute. The most training-efficient model, JEST++, achieved a new state-of-the-art on ImageNet and COCO, improving the previous state-of-the-art by over 5% on COCO. Additionally, the most compute-efficient model, FlexiJEST++, also surpassed the previous state-of-the-art on average while using 9 times less compute. These results demonstrate the effectiveness and efficiency of the JEST method in accelerating multimodal learning and achieving state-of-the-art performance with reduced computational resources.
What are the limitations or drawbacks of the method?
The limitations of the method include the reliance on small, well-curated reference datasets to guide the selection of batches within larger, uncurated datasets. This dependency on external datasets may restrict the method's applicability to scenarios where such reference datasets are not available or do not adequately represent the target distribution of downstream tasks. Additionally, the method's effectiveness is contingent on the quality and representativeness of the reference datasets, which may not always align with the specific requirements of diverse downstream tasks. Furthermore, the method's reliance on online batch selection may introduce computational overhead and complexity, especially when scaling up to larger datasets or more complex multimodal learning scenarios. Lastly, the method's performance gains are primarily demonstrated in the context of multimodal learning tasks, and its generalizability to other domains or tasks remains to be fully explored and validated.